In this video, we're going to look at Lewis acids and bases. At the beginning of chapter 14, I said that there was 3 common theories for acids and bases: Arrhenius theory, Bronsted-Lowry, and then Lewis acid and bases is our third. I do want to review the first 2 real quick before I jump into Lewis. So our Arrhenius theory, we had said that this was the most limiting of our theories, right? This is the one that said to be a base, it has to have a hydroxide ion, right? An Arrhenius base is going to be something that dissociates to produce hydroxide ions. So something like ammonia, NH3, could not be a base according to this theory. So it is pretty limiting, right? So this one is our acid is going to ionize to produce hydrogen ions, so H plus protons, in aqueous solution. So HA, put it in water. One of our products, when it ionizes, is H plus, making it an Arrhenius acid. Our base, I just said the definition of this one, it's going to dissociate to produce hydroxide ions in aqueous solution. So M for some sort of metal cation, hydroxide, going to M plus and OH minus. So again, a very limiting theory. If it doesn't have a hydroxide ion as part of it, it can't dissociate to produce one. So a lot of things that would be Bronsted-Lowry bases are not Arrhenius bases. Most Bronsted-Lowry acids are also Arrhenius acids. Remember, an acid, according to the Bronsted-Lowry theory, and we'll write this down here in a moment, are things that are going to donate a proton. So it has to have a proton to donate, which means it can ionize to produce one. So most Bronsted-Lowry acids are Arrhenius acids also. It's the bases where we run into that difference. So Bronsted-Lowry. So according to this one, our acid is going to donate a proton to another substance. Our base is going to accept a proton from another substance. So again, it doesn't have to have a hydroxide ion as part of it anymore. It just has to have the ability to bond to a proton. Remember that H plus hydrogen ions or protons don't have electrons. So my base does have to have a lone pair of electrons to be able to accept that proton, right? If it's going to bond to a proton, it's going to provide the electrons to provide that bond. An example here, we'll use HA for our acid again, but this time I'm just going to use B for my base. I don't need to have hydroxide anymore. And HA, right, the hydrogen ion is going to be given to the base. So I'm going to end up with A minus plus BH plus. So this was my acid, my base, and then we did define conjugate acid-base pairs, A minus being my conjugate base, right? It differs by one proton and one proton only from HA. And then my conjugate acid differs by one proton and only one proton from my base. And they're not always at equilibrium, but often they are, right? If my acid or base is weak, it would exist in equilibrium. If they're both strong, it would not. And then that brings us to our third theory, Lewis. And this is actually our broadest theory, right? Both Bronsted-Lowry and Arrhenius do require the acid to have a proton. Lewis acids do not have to have a proton anymore. They just have to have the ability to accept a lone pair of electrons. So it's kind of, if you think about Bronsted-Lowry as donating and accepting protons, Lewis is going to be donating and accepting electrons instead. So my acid is going to accept an electron pair. my base is going to donate an electron pair. So the donator and the acceptor in the acid and base for Lewis versus Bronsted-Lowry are the opposite, but the charge on the particle that they're donating and accepting is also the opposite, right? So a Bronsted-Lowry acid is donating something that's positively charged. Lewis acids and bases are accepting something that's negatively charged. And then I had said a few minutes ago that a Bronsted-Lowry base, right, has to have a lone pair of electrons, right? If it's going to form a bond to a proton, right, and we can use ammonia as our example. Ammonia is trigonal pyramidal. I do have a lone pair on here, and if I'm going to add a proton to it, we'll just use H plus to form ammonium ions. Kind of a mess here. It now has a positive charge, right? These electrons in that new bond, right, between the proton, this proton is adding to this molecule, right? It's forming a bond to that nitrogen. And those electrons that are forming that bond, remember these lines are electrons, are coming from my base, right? It's those electrons. Those electrons are grabbing onto that proton. So if we want to think about this from the Lewis standpoint, right, this is my base. It is accepting a proton, but it's also donating those electrons, right? It's giving them to that hydrogen ion so it can form this new bond. And then this proton, right, this is accepting electrons. It's taking these electrons from ammonia. It is a proton. It doesn't necessarily have to be. It just has to have the ability to accept protons. So a little bit more information on those. A Lewis base, I'm going to talk about bases first just because they're a little bit easier. These need to have at least one lone pair of electrons. And again, I'm not writing this down, but I do expect you to know it. So if you're not writing it down, you should, right? Our Bronsted-Lowry bases also have to have a lone pair of electrons. So a Bronsted-Lowry base is going to be a Lewis base and vice versa, right? If they're going to bond to something that doesn't have electrons, they have to have a lone pair to donate. So my base needs to have at least one lone pair of electrons. My acid no longer needs to have a proton, right? If we go back up, my Arrhenius acids, right, are going to produce a proton. My Bronsted-Lowry acids are going to donate a proton. So Bronsted-Lowry acids and Arrhenius acids are essentially the same thing, right? If it's a Bronsted-Lowry acid, it's also an Arrhenius acid, but it's not always going to be a Lewis acid anymore. I no longer need a proton. I just have to be able to accept an electron pair. Often it does have one, it just doesn't have to. So what it needs to have a relatively low energy empty orbital that can accept the electrons. Or a polar bond to hydrogen. Because if it has a polar bond to hydrogen, we can break that bond, and then I have H plus, which is an empty orbital, right? Remember H plus, I have one proton, 0 neutrons, and 0 electrons. So the s orbital, right, for hydrogen is empty. There's no electrons in that s orbital. So if I can break a bond to hydrogen and have H plus by itself, then I do have an empty orbital. So essentially this part is a way to get to this part if you don't have it. An example of a Lewis acid that doesn't have a proton, we could look at BF3. So again, we need to go back and we need to remember our information from 151. If I draw the Lewis structure for this, I have boron in the middle, and all my fluorines have their lone pairs. And this is what I would get. Boron was one of those atoms that is okay with 6 electrons. If you were to figure out your total number of electrons, go through your Lewis structure rules, this is what we're going to get. And this is my finished structure. Again, boron's okay with just 6 electrons, right? It would be trigonal planar, would be its shape, if you were to look at its molecular geometry. So all of those bond angles would be 120 degrees. And if we look at the hybridization of this atom is sp2 hybridized. And again, this was something that you would have learned in 150 or 151. So remember, if it had 4 electron groups, we said it was sp3 hybridized, 3 electron groups sp2. I'm just picking a couple, 6 electron groups was sp3d2 hybridized. And when we formed sp2 orbitals, right, we took our 1s orbital, and then we have 3 p orbitals, and we take 2 of those and combine them, right? And that's why it's called sp2, because we're taking 1s in 2 p's. So when we hybridize those, we end up with 3 sp2 orbitals, right? I have 1 here, 1 here, and 1 here. So I get 3, right? The number of unhybridized orbitals I combine are the number of hybridized orbitals I get. Because I'm taking 1s and 2 p's, I'm calling it sp2. And then the important part, I mean, it's all important, I guess, is this thing left over, right? I have a p orbital left over. And that orbital in this structure is empty. If you have a pi bond, it would be involved in that pi bond, but here it's just plain empty. So if something is sp2 hybridized, it has an unhybridized p orbital. And in this molecule, it's empty. If we were to draw its orbitals, and again, we're going back to 151 here. So I'm drawing this molecule in the plane where it's coming in and out at us. So instead of drawing it in the plane of my iPad or the plane of your screen, it's coming in and out. So this wedged one's coming out of the iPad or out of the screen at you. This one's going back behind. And then those bonds, right? This bond right here is the overlap between fluorine's orbitals and boron's orbitals, right? And this would be an sp2 orbital overlapping with an sp3 orbital. But then perpendicular to that, I have this p orbital that's empty. So because, right, boron trifluoride has an empty p orbital, that makes it a Lewis acid, right? It has a relatively low energy empty orbital that can accept electrons. And you wouldn't know that it has an empty orbital if you don't remember the hybridization, right? If something's sp2 hybridized, it does have an unhybridized p orbital. It's not involved in a pi bond in this case, so it is empty, making BF3 a Lewis acid. Another example, silver. Just plain silver with silver cations, I should say, silver with a charge. I do have an empty orbital there. It can actually bond. And we looked at these in the last video when we were talking about complex ions. I'm just gonna draw this a little differently, right? We were bonding it with ammonia, right? 2 ammonia molecules. So remember, ammonia has that lone pair on it, so it's my Lewis base. If you have a cation like this, it usually has an empty orbital. It has a positive charge. So this is my Lewis acid. And we end up forming 2 bonds between silver and ammonia. If you were to draw out the structure, it would look similar to this. Both of those nitrogens would be tetrahedral. I'm not drawing it very well, but you would end up with this. So what we're doing is we're actually taking these electrons from ammonia and we're giving them to silver. So ammonia is donating electrons, silver is accepting those electrons, and we're forming these new bonds, making this a Lewis acid, right? Because it can accept those electrons. I do realize that these are a little trickier to recognize. Kind of the typical problem that I would give you is I would give you a reaction, and then you would have to identify which is the acid, which is the base, using Lewis, and then also be able to define the definition, like be able to define them, know the definitions. So kind of if I was to give you CH3 and Br minus, and we're forming CH3Br. And then I ask you to identify the Lewis acid and the Lewis base. And sometimes it helps if you draw them out, if you go back and draw your Lewis structures. So bromine has 3 lone pairs on it. Here I have carbon bonded to 3 hydrogens. If you do your total electron count, right, I have 4 for carbon. I have 1 for each hydrogen. There's 3 of them. That gives me 7 electrons. Because it has a positive charge, I have to subtract 1. Oops. So that gives me 6 electrons total. So when I look at this structure, I have 2, 4, 6 electrons. So I've used up all of my electrons. So carbon in this case is non-octet. If you do your formal charge calculation, carbon has a formal positive charge. It has those 3 bonds, right? It means it is sp2 hybridized. It does have an empty p orbital on it. And even if you didn't see that, hopefully you would notice that it is electron poor, right? It's not octet. I don't have any lone pairs on that carbon. So just even as a matter of elimination, right? If you're trying to identify which is the acid and which is the base, CH3 cannot be the base, right? If we go back up, my base needs to have at least 1 lone pair of electrons. So again, even if you don't recognize that this has an empty p orbital, do recognize that it does not have a lone pair. So just as a matter of default, right, this has to be my Lewis base. It has lone pairs, which means this is going to be my Lewis acid, right? Acids react with bases. They both can't be bases, they both can't be acids. So if you can identify the base, the other one is going to be the acid. And then just if we look at our product, right, I have my 3 hydrogens and then it's bonded to a bromine. So what's happening, right, one of these lone pairs from bromine is bonding to that carbon. That carbon's accepting it. That's that new bond. So again, know the definitions, right? Lewis acid is accepting an electron pair, Lewis base is donating them, and then given a reaction similar to this, be able to identify which is the acid and which is the base.